So we've talked about Coulomb's law and how it predicts the force interaction between two charged particles. We've also talked about the principle of superposition, which tells us we can do the individual calculations separately and then superimpose the solutions on top of each other just by adding the x and y components. Now, what we're going to talk about next is electric fields. So an electric field is defined as, it's a vector just like the force is a vector, and it's equal to the force on force per unit charge. Okay, so what does that mean? Well, let's say we have a charge, and let's say it's positive, and it's 2 microcoulombs. So that's the charge value for that point. And what we're going to say is that there's a field around this charge, and if we place a small positive test charge, it's called the test charge, and the test charge has a really small charge called Q. It's small such that the presence of the test charge doesn't change anything. And so because there's an electric field around this point, this charge here, the 2 microcoulomb test charge, if we were to bring this test charge in from infinity to here, and the question is, what is the force acting on this test charge? So the electric field is a way of calculating the effect of a single charge initially on its surroundings. And you assume that there's nothing around the surroundings except this little test charge, positive test charge. That's what the Q is in the denominator. Now the force we're talking about is the Coulomb force that we just calculated. So we can, for F, we can put in K sub E, the Coulomb's constant, times the magnitude of, let's call this Q1 and this Q test. So the force is going to be the magnitude of the charge in question times the magnitude of the test charge divided by the distance between the test charge and the actual charge of interest here. So there we go, that's the distance like that right here. So that's R. And then we divide all of that by Q. The Q is the test charge. So you can see these cancel out, and therefore the electric field, the strength of the electric field, or the magnitude of the electric field, which is the magnitude of the force, divided by this test charge, is just equal to Coulomb's constant times Q1 divided by R squared. So the electric field magnitude is just the force magnitude divided by this positive test charge. And as a consequence, because it's positive, the force, the electric field, actually the electric field at this point in space, which is a distance R from the charge, is, so that's the R vector. So it's an R vector from the charge to the position we're trying to figure out the electric field at. The actual electric field vector is like this. So it goes straight in line with the straight line between the point in question and the position in space we're trying to find the electric field. So this is an electric field vector. The magnitude, meaning the length of this, is the magnitude of it. And that is equal to Coulomb's constant times the charge here divided by R squared, where this is R is not a vector, it's just the magnitude, it's just the length distance. So you can see that as I get closer to the charge that I'm trying to determine the electric field around, the vector is going to get longer. So let me do that. Let's make it Okay, hold on just a second. For some reason my thing wasn't working there for a second, but now it's working again. So if I wanted to know what the electric field is at this point due to this charge, it's going to have a direction away from the tester. So if I draw a line from here to there, in this case I need to move it over a little bit so that it's lined up. The length is actually going to be longer because I'm closer. And if you were to go further away, and if I went out here, then the distance r is further, but each of them are aligned directly with the point. So that aligns like that, and that aligns like that. So that one's not quite right. Let me move that over here. Okay, so they all radiate around a single charge, a single positive charge. The electric field vectors point away from the positive charge. And as you get closer to the charge, the vectors get longer. And as you go away, the vectors get shorter, and they get shorter as a function of 1 over r squared. So we call this an inverse square law because inverse means 1 over, and we're squaring the thing that's in the denominator. And another example of the inverse square law is gravity, gravitational force. It's divided by r squared as well. Okay, so this is it. As far as the direction of the vector, we would use the geometry of the radius, the distance. So what we would do is we would break this up into this r vector into 2 vectors like this, which would create a right triangle. And from that right triangle of the dimensions of this direction of the radius vector, you'd have an r sub x and an r sub y, and you get an angle theta. And that angle theta is also the angle that the electric field vector makes with the horizontal. So this theta is equal to that theta. So if you wanted to know what theta is for this vector, you would find out what theta is based on the triangle involving dimensions. So you have r sub, the inverse tangent of r sub y over r sub x. That would give you the angle. And then you can then use that angle here to calculate the x component of the electric field, which would be the magnitude of the electric field, which is what we calculate here, times the cosine of the angle theta, and E sub y is equal to the magnitude of the electric field times the sine of theta. And we would have to have a plus or minus sign, and again that would depend upon what we observe. In this case we'd have both the positive E sub x and the positive E sub y, because if you break this vector, the electric field vector, into its components, it's going to have a positive x and a positive y component. But over here, if we were to draw the vector here, in this case it's going to have a negative x component and a positive y component. And this is all based on how we define a coordinate system. This is x, this is y, positive x, therefore this is negative x. So that's how it works. Very similar to the force. The only difference is that rather than being a force, it is a force per unit charge, and that's what the electric field is. And there's an example showing you how to calculate the electric field, very similar to calculating the force. The advantage is that once you calculate the electric field at this point, to calculate the force due to another charge that I bring in to this point, all I have to do is multiply the force, the electric field, by the charge here that's going to interact with the fixed charge. So if this is 3 microcoulombs, I would multiply the electric field times 3 microcoulombs. If it's negative 10 microcoulombs, then I'd multiply the electric field by negative 10. And so it allows us to have more flexibility. Now the principle of superposition also works for the electric field. So if you were to have a charge here, let's say it's 2 microcoulombs, and you calculated the electric, let's call this point object 1 or charge 1. If we found out what the electric field vector was at this point, which it would be a vector pointing it directly away, so that's the electric field vector due to charge 1. And if we then had a second charge, which is negative, because it's negative, the electric field is going to be pointing towards it. It's a little bit closer, so I'm going to make it a little bit longer. So that would be the electric field vector due to point number 2. And then if I wanted to find the electric field vectors due to both of these charges, then I would just use the principle of superposition, which means that I just add the vectors together. And then I have the resultant vector, which is going from tip to tail to tip here. So that's my electric field vector due to 1 and 2. Or what we do with the principle of superposition is we would have an E sub x for charge 1, which would be the magnitude of the electric field vector due to the 2 microcoulomb charge times the cosine of theta. And that angle theta would be this angle between the horizontal and the vector 1. And E sub y1 would be equal to the magnitude of E sub 1 times the sine of this angle theta. And then you'd have a second angle going to this, so that we'll call it alpha. So E sub x2 is going to be equal to the magnitude of E sub e2 times the cosine of alpha, and E sub x, or E sub y2, which is a y component of that vector, is e2 times the sine of alpha. And the principle of superposition says that the effect of both of those in the x direction is you just add the effect due to charge 1, 2 microcoulombs, and whatever this is, I didn't say what it was, let's say negative 4 microcoulombs. So we add the x components together to get our total electric field at that point. And you do the same thing in the y direction. You add the y components together. So that's the principle of superposition as applied to electric fields. So we're going to talk about conductors in electrostatic equilibrium. So equilibrium means that nothing is moving. So we've talked about the force due to the interaction of charges, different charges and like charges. But at some point, a conductor will come to a situation where there is no further movement. So you might introduce some kind of electric field which pushes the electrons through the conductor and moves the electrons. But at some point, it's going to come to a static condition. So let's just draw a conductor. So the conductor is a, have we even talked about conductors yet? Is that chapter 20? Anyway, if we haven't, we'll talk about it. Anyway, conductors are materials that will conduct electricity, allow for the free movement of electrons. So there's just some body. And let's say we have excess negative charge. So what will happen is the excess negative charge will go to the surface. There's 4 rules about charges in conductors based upon where they're located and other important things. So one of the rules is that the excess charge, which in this case are negative charges, go to the surface of the object. So if it's a sphere, it goes to the surface of the sphere. If it's a car made out of metal, it's going to go to the surface of the car, meaning the outside surface of the car, not the inside surface. And the reason is because if you have excess charge, they're going to be pushing against each other because they're the same charge, and they're going to be moved away until they can't go any further. So they're going to go to the surface. If they went out of the surface, then you'd have sparks, but in this case we don't have sparks. So the 4 rules are, number 1, this is on page 513. It says that the electric field is 0 everywhere inside the conductor or the conducting material. Why is that the case? Well, it has to do with equilibrium. Because if there was a change in electric field, or if there was an electric field at all, the electric field is defined as force per unit charge. So if there's an electric field, there's a force. If there's a force, then there's going to be movement of the electrons. So this has to equal 0 so that force is equal to 0. If you go back to mechanics, equilibrium is when the sum of the forces equals 0. So that's the requirement. So if this is a solid conductor, the electric field at any point is equal to 0 inside. The second one is that the charge, the excess charge, we'll say, the excess charge is on the surface. We just talked about that one. Why is that? Because I always use the analogy of these are people that have an odor, but they can't smell. Well, yeah, they have an odor. They don't know they have an odor. I think everybody else has an odor. So they just try to move as far apart from each other as possible, which ends up being the surface. It's kind of like if you were in a room like this, and people are mingling around, and then they start saying, oh, that person kind of smells. I'm going to move away from them. So they move away. And they say, oh, that's a little bit better, so I'm going to move. So they keep moving because they're feeling like, oh, it's not so bad. And they hit the walls, and that's as far as they can go. So everybody moved to the walls. The third one is that the electric field outside the conductor, or the conducting material, is perpendicular to the surface. It kind of relates to the first reason. Because if we looked at the surface, kind of zoomed in on the surface, and there's an electron that's here, there's another electron that's there, there's an electron that's there. If the electric field at the surface was not perpendicular, it would have two components. It would have a component perpendicular, and it would have a component parallel. And this parallel component would cause the electrons to move. So these electrons are going to adjust their position horizontally on the surface so that the electric field, the perpendicular component of the electric field disappears, and the only component is the one that's, the parallel component is the one that's going to disappear, and all that's left is the perpendicular one. And then there's no force acting on these charges on the surface. And the fourth one has to do with, I'll just read it, on an irregularly shaped conductor, so meaning something that's not round. The charge accumulates at sharp points where the radius of curvature of the surface is smallest. So, let's say they have excess positive charge, which we have in the surface, And because the surfaces has about the same curvature, they're about the same distance apart. But as they get right here where it's really sharp curvature, then there's more charge there. And that's kind of why you have a lightning rod, not a lightning blob. Because if you have a lightning rod, you have a sharp end. And so the excess charge exists there, and then you have the cloud up here, and it says, oh, where can I find some excess charge? It's accumulating right there, so there's your lightning. If you just had a sphere like that, then it would be less likely to find this. What you're trying to do with a lightning rod is you want it to go through the lightning rod. You got your house. So here's your house, roof. And you don't want to hit your roof. You want it to hit a lightning rod, and then the lightning rod has a conductor which carries it to the ground. So here's our lightning rod with a nice sharp point to it, and it's connected to a wire that runs down the house to the ground here. So there it is in the ground. So it looks to this sharp point. So the lightning comes here. This lightning rod, all the electrons go through the lightning rod, down through the wire into the ground. If you had a lightning blob like this, nice round thing, you'd say, okay, well actually you'd say, oh, that's even has a nice sharp corner there, so lightning's going to go here. It goes, instead of going nicely to the ground through the conductor, it's going through this insulator. It gets hot, it burns up, and then all of a sudden you get a fire going here. Fires. Okay. That's all because of this rule. Okay, this discussion is about electric flux. And electric flux is useful in talking about a concept or a law called Gauss's law. And I'm just trying to get these things to, okay, so if we have an area in space, and we have what these lines represent are electric field lines. So this is the electric field. So if you were looking at the vector, the electric field vector in this case, the length of the arrows would be the magnitude of the electric field, and the direction of the vector would be the direction of the magnetic field. In this particular case, the electric field lines are perpendicular to the area. Another way of looking at this is if we define the area as a vector, we would have, what we would do is it would look something like this. So this is your area vector. So the magnitude would just be, in this case, width times the height for a rectangle. And the direction would be a direction perpendicular to the area. So it's pointing straight out from it. In this case, it's aligned with the electric field. Whereas if we look over here, which is a case where this is our area, the area vector would actually be pointing out perpendicular in this direction. So I guess it's angle theta. But between the area and the area vector, it would be 90 degrees. Now, what we're talking about is electric flux. And flux is kind of like a movement of something or a quantity. In fluid mechanics, we would think about mass flux, which is just mass flow rate, kilograms per meter, kilograms per second. So the same kind of thing applies here. What we're having not something flowing through here, but we're having electric field vectors go through here. In this case, we're assuming it's constant. And so the flux, which we use the symbol phi, for is just the product of the electric field, the strength of the electric field, basically, and the area. So the area would be the height times the width, and the electric field would be some value in something at a page. So the electric field, and this would be the magnitude of the electric field, would be equal to Coulomb's constant times Q times over R squared. There would be something that was causing this electric field, whatever that is. So it's due to a distribution of charges, probably some positive charges over here and some negative charges over there. And in this case, we have a situation where we actually have a constant electric field between 2 points in space. And so it flows through this area. And the units for electric field are newtons per coulomb, because it's force per unit charge. And the units for area are meters squared. So we'd have the units for flux would be equal to Newton meters squared per coulomb. And as far as electric flux is concerned, we don't give a special name to it. In magnetic field, we give a special name to it, but for electric field, it's just the units that make up the definition. So the stronger the electric field through a given area, the larger the flux is. Or given electric field, if you have a larger area, you're going to have a larger flux. Now, what happens if the area is not aligned with the direction of the electric field? Well, what you're going to do is there's two ways of looking at it. You can take the component of the electric field in the direction of the area, or you can take the component of the area in the direction that's perpendicular to the electric field. So that's what they're showing here, is that this area back here in the kind of orange shade is this area projected onto the y-axis. So if you took a light and you shined it on this side and you had a wall behind here, you'd see just this smaller area. If you rotated it all the way up so it was perpendicular, you'd get a larger area. And of course, if you rotated it completely flat, then you would see no area if the thickness of the area is 0. So it's showing it being very small here. It's the thickness of the line. So in that case, the flux is equal to the value of the electric field, the magnitude of the electric field, times the area, which is just the width times the height, and then you multiply by the cosine of theta. You can check when theta is 0, meaning the angle between the area vector and the electric field vector is 0, which is what happens back here. They're both aligned in the same direction, so the angle is 0. The cosine of 0 is 1, and you revert back to the simple definition. Now, from a and flux is a scalar. So electric flux, electric field is a vector, but electric flux is a scalar. It's just a number. And from a calculus standpoint, what you do is you say that the electric flux is equal to the integral of the electric field dotted with the dot product with the area vector. So if you have a varying electric field over an area, then you can use calculus to figure out what the flux is. If the electric field is constant, then you can take that outside the integral, and the integral of dA is just the area. And you get here. What the dot product represents is if you have a vector like this, let's say that's your area vector, and this is your electric field vector, this direction. The dot product represents this. So what this is the projection of the area vector onto the direction of the electric field vector. This is the angle theta. So if I wanted to find the product of these two, I would find the product of the length of this vector times the projection of the area onto this vector, which is just going to be the total area here, which would be the length of this vector, times the cosine of theta, which would give you this adjacent side to the angle. So then you multiply that vector length times that vector length, and you get the total vector length, which it's not a vector because what we're doing here is multiplying the length, the magnitude of this vector, not the vector itself, but the magnitude of this vector times the magnitude of the projection on there. So that's the calculus version of the whole thing. So that's what an electric flux is. Okay, we're going to talk about electric flux. And this relates to electric fields, electric field vector. So let's say you have a bunch of positive charges over here. And you have a bunch of negative charges over here. The electric field lines between these positive charges and negative charges are going to not exactly look like this, but it's going to give you a fairly straight line between the two. And the more charges you have on both sides, the more this approximates. This is a correct assumption. So those are electric field lines. And you can have this two-dimensional. You can have another stack of them back here that go back into the paper, and you can have another stack of negative charges. So you have a three-dimensional arrangement. So you have these electric field lines. And we could say that let's assume that it's uniform. So it's just going to be, no matter where I go here, the electric field value is going to be the same. It's going from left to right. Okay, now if I were to draw it looks like this. What this is supposed to represent is like a hoop, but it's not going, a hoop going like this would be perpendicular to the page. Whereas this, if I drew the hoop like that, you'd be looking at the edge and everything would be going through. This is to try to give you a perspective drawing where you kind of see both dimensions. So you can think of this as a hoop, and these lines are going through the hoop. And right now I've made it so they're perpendicular to it. Now the hoop has certain properties. It has an area associated with it. And let's say this is a circle, but it's rotated at an angle. So this has a radius, some radius value. And so this has a value R. Now because this is a hoop, even though it doesn't look like it, this is also R. It's just because of the way we're looking at it. So because we're kind of looking at it as if it was rotated around. Okay, so this hoop has an area, which is going to be equal to pi times the radius squared. So that's the radius of a circle. I mean, the area of a circle. So that's the area. And if these lines are perpendicular to this area, then the electric flux, the electric flux, which you use phi. Later we'll use phi, we use phi sub E to stand for electric flux. Why? Because there's also magnetic flux. It's equal to the product of the electric field, the magnitude of the electric field, times the area. And this is because the area and the electric field are perpendicular. Perpendicular. So this is specifically for that. So that's a flux. Now these electric field lines, do they exist or not? I mean, they are a device that help us calculate forces due to electric charges. Are they there? Yes. Are they arrows? No. It's kind of like a gravitational field. The gravitational field is from us to the center of the Earth. We don't see it, but we see the effects of it. Same with the electric field. The electric field, we can see the effect of it when we have charged particles. So one way, an analogy is if you have a pipe. So here's a pipe, and that's the ends of the pipe. And you have some fluid flowing through there. Now you don't see arrows going through there, but you do see these represent the velocity of the fluid going through there. And so if we were to take that velocity, which is equivalent to the electric field, and we were to multiply by the area, that would give us we would call it a volume flow rate. If we multiply by the density of the fluid, that's called the mass flow rate. So it tells us how much water is flowing through here. So you can kind of think of this as the amount of electric field that's flowing through this area. You know, if we had a round pipe, this area that we're considering here is pi r squared, the radius of the pipe here. It's just some arbitrary area that we've picked in space to look at. So that's what the electric flux is for the simplest case. Now, if I were to draw these electric field lines from the top, and so this is looking down, what we were looking at was a case where so here's my area. We were looking down where this area actually is lined up, and if I rotate this thing around, what we were looking at was this case where the electric field lines come through and they go through the hoop. Now the hoop can be at some angle. And if the hoop is always all right like that, there's no flux going through this hoop because it's all going parallel to it. And if I'm at some angle, then I get the most I get is when they're perpendicular to each other. I get zero flux when this is like that. And in between I get some value. And it depends upon the way we define the area. So the area of this hoop is actually the area vector of the hoop is outward from the hoop. And this is my electric field vector. So from a vector standpoint, we take what's called a dot product of the electric field vector. So the flux is not a vector. The electric flux is the dot product of the electric field vector and the area vector. When you do a dot product, you get a vector. I mean, you get a scalar. So the dot product of two vectors gives a scalar. Scalar dotted with a vector dotted with a vector is a scalar. This is just a number, so there's no arrow. Now it turns out if you take the angle between the electric field and the area, this is theta, it turns out that the electric flux is the magnitude of the electric field times the magnitude of the area times the cosine of theta. So the maximum flux phi sub E occurs when theta equals 0. That means this thing is aligned like that, and this comes down like that, and the angle is 0. The minimum flux occurs, so the cosine of 0 is 1, so we get the maximum. In this case, where it's aligned like that, the angle between the electric field lines and the area vector is 90 degrees, which gives you a 90-degree angle. The cosine of 90 degrees is 0. So you get the minimum when it's aligned in that direction. and if it's aligned in any other direction, so that's my hoop, that's my area, which is perpendicular to the surface. This angle theta is the, so then you have somewhere in between. So the minimum flux, which is 0, is when theta equals 90 degrees. Okay, so that's the idea of flux. And there was one more thing I was going to tell you. I know. If you had a three-dimensional, like a box, so here's my box, it's a cube. The question is, do you have positive or negative flux? So relative to this box, you're going to, if you have the electric field lines going, the electric field going this direction from left to right, on this surface, the left-hand surface of the cube, the flux is positive because it's going in, and on this side, where it's leaving this surface, the electric flux is negative. And the other surface is 0 because the surfaces are parallel to the direction of the electric field. So we have positive flux coming in the left surface, negative flux leaving the right surface. If this is a constant electric field with a cube, the net flux is 0 because you have the same amount coming in the left as you have leaving the right. And then the other surfaces, top, bottom, front, and back surfaces, there's no flux because we're under this situation where the angle of the area is 90 degrees to the electric field vectors.
Okay, this is chapter 16, and the title is Electrical Energy and Capacitance. So if you remember back to the Newtonian part of physics, we had Newton's second law, which said force equals mass times acceleration. We solved a lot of problems like that. And then we also had conservation of energy, which said the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy equaled the work. So we had force considerations and we had energy considerations. We're going to have the same thing here. We've done the force considerations. We've looked at the forces between charged particles. We've talked about electric fields, which are our convenient way of representing the effect of charged particles. And then we're going to talk about energy. So it's the energy stored because of the relative position of two charges is a potential energy, just like gravitational potential energy is that way, spring potential energy. And now we have what would be electrical potential energy. And if you remember about gravitational potential energy, let's just remember gravitational potential energy was equal to the mass of the object times the acceleration due to gravity times the height above some reference, with the key being reference. So when we were interested in the change in gravitational potential energy, we were interested in the change in height. So it's delta H, not H. So the absolute potential energy wasn't as important as the change in potential energy, and therefore we had a change in height, which didn't matter, whether we set the height equals 0 here, we set it equal to 0, as long as we had this common reference point, the change would be the same. So if I went from this height to this height, this delta H would be the same whether I use this as the zero value or this is the zero value. And the same thing applies for electrical potential energy. Now, the way we determined the change in potential energy in general was we had some final potential energy and we subtracted some initial potential energy, and that turned out to be equal to the negative of the work that's done during that change. So we use that definition to come up with the electrical potential energy. And what we look at is a scenario that looks like this. So we have two plates, and they're charged. So let me just clone this. So we have two charged plates. One plate has positive charge on it, and one plate has a negative charge on it. And because of that, there's an electric field that exists between these two charged plates. And the electric field goes from the positively charged plate to the negatively charged plate. So here's our electric field. And we're going to assume that it's uniform. So assume the electric field is uniform, which means constant in that space. Now, if we take a charged particle, we're going to use a positively charged particle because we've always used that in the past, used positive charges as our test charge when doing this. So here we have a positively charged particle. And because of this electric field, you're going to have these positively charged particles are going to push this away to the right, and the negatively charged particles are going to pull it to the right. So you have both a push and a pull. And so if I let go of this thing, it would if I had this stationary and then I let go, it would move like that, just like a particle moves in gravity. And in gravity, the way the thing falls is going to be the direction where you have a decrease in potential energy. Okay. So this object here has a charge Q. So let's put that in there too. Let me move this out. So we'll give it a couple of properties. So and we'll group those together. So this has some charge Q. And there is an electric field that's pushing this. So there's a force that's pushing this. And if you remember, the electric field is equal to the force per unit charge. So the force is equal to the electric field times the charge. And since this is constant, since the electric field is constant between these two plates, the force acting on this particle is going to be the value of the electric field times the value of the charge. And it's going to push it to the right. Now, just like if we held something in the air and we have our ground and we let this go, if we just move it from one level to another, we have a change in gravitational potential energy. So the same thing applies over here. What we're going to do is we're going to move this charge a distance, delta x, from left to right, just like we'd have a delta h. So this is delta x. It has some initial value, x sub initial, some final position, x final. So as we move this charge from here to here, there's going to be work that's done because the movement, direction of the force is in the same direction as displacement. And what we find out is that the work done moving from point A to point B, let's call this point A, and this point B, is equal to the force moving in the x direction, so this is my x direction, times delta x. So work is force acting through a distance. Newton meters. The force is Q, the charge, times the value of the electric field, and delta X is X final minus X initial. So this is the work done. And because of the fact that the work is equal to the change in potential energy, what we can say is that there's going to be a change in potential energy due to this charge in the presence of an electric field, which is going to be equal to minus the work done from going from A to B, which is negative Q, the charge, times the electric field, which in this case in the X direction, times delta X. So that is an example of the change in electrical potential energy in going from one point to another. Now, because delta X is positive and E is positive and Q is positive because it's a positive charge, we're going to have a decrease in potential energy as we move from here to here. And again, if we think about gravity, if we move something down in the direction of the force, in the case of a gravitational potential energy, it's the gravitational force which is pushing down. In this case, my electric field, my electric force is pushing from left to right. So this decreases the potential energy. If I go the other direction, I increase the potential energy. Now, if I have a negative charge, then everything flips around the other way. So that's why the sign of the charge is important. Okay, so that's what electrical potential energy is in a constant electric field, a uniform electric field moving through a certain distance. It involves the magnitude of the charge, the magnitude of the field, and the distance that we travel. So we just talked about change in electrical potential energy. Now, if you remember back in chapter 15, we talked about force, and then we defined something called the electric field, which was equal to the force per unit charge. So we're going to do the same kind of thing here. We're going to define the change in potential energy per unit charge. And what that allows us to do is to, here, when we were dealing with forces, we were able to create this concept of an electric field that allowed us to draw electric field lines and visualize what was going on. A similar thing happens here in that the change in potential energy per unit charge allows us to think about not what is the voltage or what is the potential energy associated with the relative position of two charges in space, but it allows us to just take a single charge in space and say what is the potential energy per unit charge at a point in space. Just like with force, we initially looked at it, the force between two particles, but what we did with the electric field is we got rid of one of those particles and we said what is the electric field in this point in space. So it's the same kind of concept. And we call the change in potential energy per unit charge, we give it a name, and we call it the change in voltage. So the change in potential energy per unit charge is equal to the change in voltage. So V stands for voltage. And it turns out voltage has the units of volts. Now, what are the units of volts? Well, if you look at energy, energy is joules, and charge is coulombs. So a volt is equal to 1 joule per coulomb. And what it allows us to do, we'll find out later on, is if we have a single charge, say it's 2 microcoulombs, and we want to know what is the voltage in space associated with that charge, then we can calculate that. Now, we don't know what that equation is yet, but we'll come to that. First, we're going to look at our particular case here of a charge existing in this constant electric field. And what we see is that what we saw was that the change in potential energy was equal to negative Q, the charge, times the electric field times delta X. So if we'll find out that the change in voltage as you move a particle in this constant electric field is equal to negative E times delta X, because if we divide both sides by Q, so if we take delta PE, potential energy, divided by Q, which is the change in the voltage, you get negative E times delta X, or negative E sub X. So that allows us to calculate the corresponding change in voltage in going from point A to point B. All you do is, if you know the electric field value, which is constant in this situation, times the distance traveled, then you can you can calculate that. Now, another thing about the units is here it's joules per Coulomb. Am I getting that right? Potential energy is joules. So the electric field, if you remember the electric field, the original units are force per unit charge, which is going to be newtons per Coulomb. Now, it turns out that if you solve here, you'll find out that it's also can be defined as volts per meter. So 1 Newton per Coulomb also equals 1 volt per meter is the electric field. We'll come back to that later. You'll find out later that the voltage is equal to the change in voltage is equal to the change in electric field. That's incorrect. What we'll find out is the electric field in a place where the electric field is not constant. So this is up here. So the electric field in the x direction will be equal to the change in voltage divided by the change in x. So you're actually able to calculate this from the change in voltage between 2 points. Okay, so that's what voltage is. Change in potential energy per unit charge in a constant electric field is just equal to, where am I here? It's just, lost where it is. It's equal to negative the electric field times the change in x. So our previous discussion was about the change in voltage in a constant electric field, which came from 2 parallel plates that were charged. Now we're going to talk about electrical potential, which we call the voltage. So there's electrical potential energy, which is PE, called E maybe for electrical potential energy. There's electrical potential, which is voltage, which is equal to, so the change, delta V, well, delta voltage is just the change in potential energy per unit charge. So you have to make sure you don't get these confused. So we're going to talk about both of these for the case of a point charge. So we did this for Coulomb's law. So let's say we have a positively charged particle. And what we want to know is, what is the voltage in space around this particle due to the presence of this positively charged particle, which has some charge Q. Now, just like with force and like electric field, it depends upon the distance. So we were talking about how you determine the potential energy associated, or the voltage associated, I guess you'd say the potential energy as well, but the voltage in space due to the presence of a charged particle which has a charge of Q. And so if you think about it, if we were to draw a little circle here representing some other test charge, and let's say it's positive, because we always assume test charges are positive. If you let me group these together. So as you bring these close together, the force increases with 1 over r squared. So I'm increasing the potential energy under this condition, decreasing the potential energy under this condition. Now when you get out to infinity, so you go to infinity, the force should go to 0. And what we're going to do is we're going to define the potential at infinity to be 0. And then we have this test charge that comes in. And they don't show this in our book because it's not a calculus base, but I'm going to mention it. So what you're going to do is you are going to integrate the force that's acting on this charge multiplied by dx. And you're going to integrate from infinity to some value of x, or some value of r, I guess would be probably more appropriate. So at infinity, the force is 0, and as you integrate into r. And because the force between charged particles is equal to Coulomb's constant times the two charges, so we have Q times some, we'll call it Q sub t, some test charge, divided by r squared. And r is not a radius, it's just a distance, so really we're integrating with respect to dr. These three things are constants: the actual charge, the test charge, which is just a small charge. So you can take these outside the integral sign, and what you end up with is the integral from infinity to r of dr over r squared. Okay, so that is Coulomb's constant times the charge times the test charge, and this is going to equal the work, which is also going to be equal to the change in potential energy. And when you integrate this, you're integrating r to the minus 2 dr. So you add 1 to the exponent and divide by the new exponent. So you get 1 over r. So you get k sub e q test charge divided by r, evaluated from infinity to r. And you can see that what's going to happen here is that infinity, you divide by infinity, so it's 0 at the lower limit. And the upper limit is just going to be r, so you plug that in there. So ultimately, you get the change of potential energy is due to a point charge is k sub e Coulomb's constant times q times the test charge divided by r. This is delta potential energy. So if you divide both sides by the test charge, we'll get change of potential energy per unit charge is just equal to Coulomb's constant times the charge of the particle in question divided by r. Okay, so in your book, they say the voltage is equal at any point around this positively charged particle is Coulomb's constant times the value of the charge divided by the distance. So let's just do a simple example. So let's say the charge is 1 electron, which is, or 1 proton, which is 1.6 times 10 to the minus 19th coulombs. Let's say the distance is 5 centimeters, which is 0.05 meters. And Coulomb's constant is 8.99 times 10 to the 9th. And the units for Coulomb's constant is Newton meters per Coulomb squared. So you just plug those in, and you say the voltage cutting point 5 centimeters from a positively charged particle. Just plug the numbers in. And so in my calculator, so 8.99 e to the 9th times 1.6 e to the minus 19th divided by 0.05 is, you get a really small number because we're just dealing with a proton. One charge, 2.88 times 10 to the minus 8th volts. So that's the voltage at that point. Now, if it was an electron, it would be negative. So this is a proton. An electron, you do take into account the sign. It would be negative 2.88 times 10 to the minus 8 volts. Next, we'll talk about how principle of superposition works.